Alright, so let me do demo of this freeform timed assessment for electromagnetism. You have one demo of me doing it so far. So I did take time to roll the dice or preload the dice to make sure the question that test student will get right now when I click start, it'll definitely not be the question that I've already done. I kind of looked at it. Now I promise you I haven't had a lot of time to think about the question, so this is still kind of genuine-ish attempt, but I just want to make sure, in the interest of full disclosure, I've seen the question. I know it's going to be some sort of solenoid question when I click start. So I'll click start, and 20 minutes is not a lot of time, and I do want to try to get to the circuits demo, so I'll try to go through it as quickly as I can. I will still explain some of the things, but I'll try to avoid wasting time. Now, this question might look familiar. I think I actually borrowed this from the magnetostatics set, and there's a little added part that makes it electromagnetism or Faraday's law question. So if it looks familiar, yeah, not a mistake. A good chunk of it is magnetostatics question. So many, yeah, I think I called it like a uniform magnetic fields in the previous set. So consider an infinite solenoid carrying current, all that, using Ampere's law, show that magnetic field. Yeah, so I guess so. Let me first sketch the kind of graphical portion of Ampere's law application. And whenever you are applying Ampere's law, you gotta draw me your Amperian loop. If you haven't drawn your Amperian loop, then I kind of know you're just giving me something that you memorized, not something you understood. So here, with this kind of current flowing on the right side of the loop, poking out of the screen, on the left side going into the screen. So I know magnetic field kind of points downward. That sense of direction for magnetic field is needed for choice of Amperian loop. So I'm going to choose my Amperian loop in a way that conforms to this magnetic field. So I want to make sure my Amperian loop on the inside has a portion of the segment that's pointed downward. And I have to close the loop. I can't have a single segment and call them my loop. So I have to turn 90 degrees here. 90 degrees to make sure this will be 90 degrees, and I collect the line integral on this here. And on the outside here, so to be completely correct, really what you have to do for your loop is you have to make sure that this outside end goes all the way out to infinity, because it's only out at infinity at are going to infinity that you know that your magnetic field will drop to zero, and you get no B dot DL contribution here. But I know your textbook kind of shortcuts this portion of the argument. Your textbook just says, you know, B is equal to 0 outside, and if you're using that, it's fine. If it's a shortcut that your textbook takes, hey, you're allowed to take it. So you need to have this picture in mind with the direction of magnetic fields, your Amperian loop. Let me label this as my Amperian, the way I like spelling it. It's probably wrong, but I like this better. Amperian loop. So I start out with a statement of Ampere's law. Ampere's law says that integral of B dot DL around the closed loop, this is a required part of Ampere's law. That's why I had to close it. That's equal to, so you can write it two different ways. You could either say 4 pi, you know, this version, 4 pi Coulomb constant divided by c squared times I enclosed, or you can use the mu naught I enclosed. So this is Ampere's law. So the loop that I drew, you need some specification. I need to say, all right, this is loop of height h. That this parameter allows me to quantify how much current is flowing through the loop. And the way I set the directions, this should be all positive. It should be basically h times the loop density, number of currents flowing through. So with this, I can say my right hand side is 4 pi k over c squared, and the amount of current enclosed, H times N, the loop density, times I naught. The left hand side, so technically you have to break up the integral into 4 parts. 1, 2, 3, 4. So this line integral around the closed loop really becomes, I guess, still line integral, but not a closed loop anymore. The integral around the segment 1 plus integral around segment or along segment 2, integral along segment 3, plus finally integral along segment 4. And the whole reason for all this setup is really to be able to argue that this integral is 0 because B is perpendicular to dl. For the same reason around the segment 4, it's 0 because B is perpendicular to dl. And here, this is the portion where my argument in lecture is more careful than your textbook's version. But either way, the end result is you want this to be 0. You don't want that to be non-zero. And for around 1, this is where you get, you use the translational symmetry argument. So through translational symmetry, I'll type it out here. You can say that B is constant along the segment at 1. So you can say this becomes B times dl, and you can say, oh, that's just my length of the segment, h. So that's equal to the original right hand side, h and I naught. And now you can cancel out the h from both sides. Then you get magnetic field is equal to that, which is the formula you're trying to get to. So I'll say I'll attach a figure with the Amperian loop drawn, alongside the directions of the magnetic field. You don't need to put enough in the answer to kind of anchor the details in here. So in the figure, I start with the statement of Ampere's law, right hand side simplifying to 4 pi k over c squared times h times n I naught. H is the height of the loop. On the left hand side, the integral along 3 of 4 segments are 0 for geometry reasons. And for the integral along segment 1, from translational symmetry of the setup, we can argue that the magnetic field is constant along the loop, allowing us to factor the B vector outside the integral, and recognizing that integral over segment 1, the line integral over segment 1 is just h, the length of the segment. H cancels out from both sides to give us the formula for B. There are some details that I'm skipping over, like how this is parallel to B, that allows us to simplify the dot product. I'm skipping over that. Estimate the strength of magnetic field that can be generated using the solenoid above for the following parameters. And do I give you the constants? I don't. But I think at this point I have memorized a lot of it. So, so B is equal to 4 pi k over c squared. Do I want to do it in O from alpha? Let me do it just here by hand. So n times I naught. So I'm gonna plug in all the numbers. 4 times 3.14. K is the one that I, by this point in the semester, I haven't memorized. So I'll say in basic SI units, just gonna skip all the units. So K in basic SI units is 9 approximately 9 times 10 to the power of 9 in basic SI units, divided by 3 times 10 to the power of 8 meter per second, again basic SI units, times n. Now it's gonna be length is 1 meter, total windings is 8,000, so it's 8,000 windings per meter, basic SI units, times I naught, 10 ampere. So with all those, can I do this in my head? So approximately is equal to 12 times 9, so I'm gonna call that about 100 within like 15%, times, oh wait, I forgot to square that, times 10 to the power of 9 divided by 3 squared, so 9, times 10 to the power of 16, times 8 times 10 to the power of 3 times 1 times 10 to the power of 1. Let me do all the powers of 10. So it's 9 minus 16 plus 3 plus 1. So that's minus 3. Or 9 plus 1, 10, 13, minus 16, minus 3. And then the rest of the factors is 100 divided by 9, that's approximately 10, times 8, that's approximately 100 again. Or I can imagine canceling 9 with 8. I might be off by like 20% on the too large side, maybe too small side. So it's about 100, so 100 e minus 10, or about 0.1 Tesla. It might be too large by a factor of by 20%. So yeah, that sounds about right. 1 Tesla magnetic field is super large. You basically need a superconducting magnet to generate a 1 Tesla field. Like 0.1 Tesla is respectable non-superconducting magnetic field. So I think that's right. And we'll double check. Now this radius, it doesn't affect us anything here, but it'll matter for the next part. The solenoid considered above is also an inductor. That's an inductance. So you start out with the formula for inductance, which there's at least like 2 or 3 versions you can use. Here I'm gonna use the one that will allow me to do the calculation the most quickestly. That's gonna be basically the total magnetic flux, which will include the factor of n for the number of loops, divided by current. So here, in terms of the things I know, it'll be magnetic field times the area, that's the flux of one loop, times the total number of loops, that divided by current. So calculate the inductance of solenoid with the same parameters values as B, and so on. So I guess I'll say, so starting with the value of B estimated above, it's kind of doing a couple extra things, but it's fine. Like a factor of I, it's part of B and then it'll cancel out. It's fine. It'll save me a little bit of time. So it'll be about 0.1 Tesla. So I'll say in basic SI units, 0.1 Tesla times the area. I need to say pi r squared. So approximately 3.14 times 0.18 squared, or 0.2 squared. Doing this approximately equal to so pi r squared times n. That was 8,000 divided by current 10. So that's equal to so 0.2 squared, it should be 0.04 times 3 is 0.12. So 0.12 times, so So 1 minus 1 times 1.2 e minus 1, that's 0.12 times 8e3 divided by 1e3, 1e1. So that's so 8 times that is about 10 within 20%. So 10, so 10 to the 4, subtract these 10 to the 2 divide. So I think a 10 Henry within about 20%, I think. Alright, that's for the magnetic field calculation part B, we assume that the power supply can provide up to 10 amperes, many high current limited to low voltages. Yeah. Suppose that this power supply can provide a maximum voltage of 5 volts. If our solenoid is made with ideal wire zero resistance, how much time? Ramp up the current. Okay, so I guess I will use the relationship for inductor. The voltage is given by delta V is equal to inductance, absolute inductance times di dt. So giving the maximum voltage of 5 volts gives me basically so maximum voltage gives maximum di dt possible. So maximum di dt is equal to V max divided by L. So here I think I can say 5 volts approximately equal to 5 volts divided by what I calculated above, 10 Henry. So when the units all work out, it should give me amperes per second. So I'm just going to trust the SI unit system and say it's 0.2 amperes per second. So if I'm trying to change it by 10 amperes, then I need 50 seconds to ramp it up to 10 ampere. At this rate, I need 50 seconds to ramp up to 10 amperes. Again, within 20% because the 10 Henry estimate is within 20%. So yeah, so parts B, C, and D were done just here, and A is the only thing that I need to attach a figure for. Sorry, I'm rushing a little bit because I do want to get to circuit questions, and I think I can. So let me wrap this up. I will show you the answer kit to make sure that I didn't make any mistake in my rush. Any serious mistake. Again, the numbers are gonna be off by as much as 20% that I've accepted. That's the price of doing things in your head and not on calculator, in the interest of where's my submit button? In the interest of I can't see my save progress. Yeah, submit and end. But I'll show you the answer kit to make sure that I didn't make any serious mistakes, serious physics mistake. So I did that. Yeah, so I can just save work and continue. It's gonna be 0% because it, and it's not due yet, so I don't have answer key here. Let me go in as an instructor and then show you the answer key to make sure that I didn't make any serious mistakes. This is test student's attempt. Again, doing it like a week early because of the session time that we are missing next week. So with all this, this one is just correct. You know what answer you are getting to, and all this is correct. I mean, I can show you the answer key. It just doesn't do anything different. Oh, I guess I did it on this side for that. Did I? I might have a mistake. No, I guess that's right. Yeah, because this is clockwise. Yeah, I think it's fine. I think both are fine. There's no mistake in either. Yeah, and then here I estimated 0.1 Tesla. Let's hope that's correct. Oh, yeah. Yeah, 0. Oh, exactly 0.1 Tesla. Must have gotten lucky with the numbers. Oh, yeah, yeah. So then the rest should be also fairly accurate within that. So here I estimate 10 Henry. So it should be like pretty close to 10 Henry. Okay, off by 20%. Yeah, some of the estimates I was doing, I knew. So, but within 20%. So this should be again within 20%. So did all this. It gets me. What mistake did I make? That's not within 20%. So 10 amperes, 5 volts. 5 volts divided by 10. Um, 0.2. I think from here. Wait, so in 5 seconds it'll ramp up to 1. So Imax divided by. So 10 divided by 0.2. That is 50. There might be a mistake in the code. Let's see. Delta T is Imax divided by B divided by Imax is 10. Oh wait, n squared. Oh no, that's fine. Because I had the n from the factor of b. Pi r squared. I'll just check the code here. What am I missing? I mean, I don't think a regular calculator would give me anything different, but so 5 volts divided by 8.186. Oh, I know the mistake I made. So in this division, that's 0.5 ampere per second. So yeah, okay, I made a mistake there. It's not 0.2, it's 0.5 ampere per second. So yeah, with that, yeah, 20 seconds is what I would have answered. But because of the mistake, I didn't answer 20 seconds. Yeah. But if I answer 20 seconds, that's within 20% of this. Yeah, so yeah, again, the pitfall of the mental math. Yeah, and I guess with this checking of answers, now we are 3 minutes over.